Okay, we're gonna get started in a second. It's a 15-minute presentation. You just have 15 minutes. I'll give you a 5-minute, a 2-minute, and a 1-minute warning. So just glance over to me occasionally so you don't miss those. At the end, we'll have 5 minutes for questions, and you'll have a moment to thank anyone you want. When you begin, we just ask that each of you introduce yourself, and then once you start the talk, I'll start the timer. So yeah, we can begin whenever you're ready.
Hi, we're team 17781 from Winchester College. I'm Victor.
I'm Alex.
I'm Andre.
And we also have two members that couldn't make it because of visa issues. They're Henry and Yu Yao. So before we get into the main content of the presentation, I'd just like to mention some of the unique contributions that our team brings. I think uniquely, we believe that mathematical modeling should be used to make mitigation strategies. So I think that we actually use technical computing to come up with very specific mitigation methods later in the presentation. We achieve this by data quantity, considering 3 separate sources of data, which each contain many of data points which would not be able to be considered without a tool like Python. And by data diversity, we mean like this type of data that is present means that we couldn't do it by hand or by Excel because it wouldn't be possible to clean and process this data otherwise. And by optimization, I mean we consider the computational complexity, like the NP hardness of the problem, as well as running multiple simulations such that we have a reasonably good solution. Also, when we mention scalability, we talk about the modularity of our code, which means that simple tweaks can mean that similar methodology can work in different cities. So now on presenting question 1, hot to go. This problem asks us to predict the indoor temperature given the outdoor temperature on the hottest day in Memphis, Tennessee. The method that we decided to use was Newton's law of cooling. Simply put, it describes the transfer of heat between 2 mediums over time and is basically characterized by a constant K, which we later determined to be specific to individual buildings. Why should we use Newton's cooling law? Firstly, we believe that physical principles are universal. This means that even though we use a UK data set for our temperature data, we think that physical principles hold the same anywhere. Therefore, any of the conclusions that we come to are valid. Secondly, it's more justified than only using a model which uses parameters. This is because we can use coefficients to explain what's happening, not just model the data. We think passive transfer naturally lends itself well to Newton's cooling as per physics principles. And also we think that since we're directly accounting with thermal energy and temperature, it's adjustable for human impact. So the factors we included were the change in environment temperature, the human power output registered to be 100 watts as per literature review, as well as building-specific constants, specifically affecting K by volume and surface area. We did not account for effects of windows and ventilation, as this was not given in the M3 dataset. To determine K, we basically split the data from a dataset into hour-by-hour levels and just rearrange Newton's cooling law in order to get a value for K. We averaged this across different rooms to get a reasonable approximation.
So, to determine K, we used the Loughborough housing dataset. This is a collection of indoor and outdoor temperatures for a single-family home, as well as a comprehensive floor plan, which we used to calculate the dimensions of the building. We used the temperature data in the dataset to determine K. We found that K is directly proportional to the surface area and inversely proportional to the volume. We then solved the system of equations to find alpha and beta, which generalized well across the data we used. We also found that the human power output was significant enough to change the temperature. We took this value to be 100 watts. Using the above physical laws, we found delta T, the change in temperature, which we will add to our final temperature. This code shows how we computed the temperature using Newton's cooling law. The key thing is that we did this by splitting into time segments and finding each individual temperature. Here you can see the computed temperature profiles for each building. Note that we used a standardized height of 5.51 meters. These graphs matched the behavior we expected. The fourth room on the bottom right had the largest volume, and as you can see, it had the slowest heating. We also find that humans have a minor but non-negligible effect. We analyzed the sensitivity of our model both empirically and analytically. We rearranged Newton's cooling law on the left to obtain the below equation, and we found that the sensitivity decreases as Ts approaches Tt or T0. The figure on the right supports our hypothesis that K is highly sensitive to changes.
So the second question asked us to develop a model that predicts the peak demand that Memphis power grid should be prepared to handle. So MLGW is the largest and effectively the only electricity supplier in Memphis. On the left diagram, you can see that Tennessee Valley Authority produces most of its energy, which is then given to MLGW to distribute to its customers. This energy comprises effectively all energy used in Memphis, and therefore we can assume that MLGW is the only supplier of electricity. which means that we can use its financial reports to get the data about the demand. On the right, you can see graphs for residential power usage and industrial power usage. We decided to take a look at power usage of different customer categories. And we noticed some fundamental differences between how residential and industrial units operate. Industrial facilities often have heavy-duty appliances on 24/7, whilst residential units often have energy use peak at different times of the year due to lighting and heating or cooling. This can be observed on the graphs on the right. Without splitting the data, our model would not account for seasonality in residential usage exclusively. So we decided to use Sarima and Holt-Winters models to model the demand. The study has shown that Holt-Winters models were superior at modeling less variable monthly flows, while Sarima models better forecast highly variable periods. So this is the data for our Sarima model. We predicted that summer and winter usages would follow different overall trends as time goes on. Using one Sarima for both winter and summer would merge two trends together or even kill one of the trends, which would greatly affect our final prediction for demand. Therefore, we decided to split data into summer and winter seasons and run both through corresponding Sarima models. So this is our Sarima model, and it takes 7 parameters. I'll explain how we chose all of the parameters. So first of all, we can straight away set S equal to 12 months or 1 year, as it's the length of the cycle. For values of P, D, and Q, we ran an augmented decoupler test to determine a value of D, and we plotted partial autocorrelation functions and autocorrelation function in order to determine P and Q. As for seasonal components, we used an AutoArima library for seasonal parameters. So these are the results. As we can see, Memphis City residential power demand will follow a decreasing trend in the next 20 years. This was within our expectations because Memphis had a well-established trend of population decrease. Also, our model seems to discount the effects of global warming, but actually we believe that it's not the case because a decrease in population can counteract the effects of global warming in the summer, whilst effects of global warming are still present as it causes winter consumption to decrease.
So to model the industrial and commercial dataset, we opted to use Holt-Winters exponential smoothing. This is effective when the data has a clear trend in seasonality, and notably more so than Sarima when there's less variation in the data. Here, you can see the variables we used, including alpha, beta, and gamma, which are constants which we will determine later. So Holt-Winters has 2 versions, additive and multiplicative. It was not necessary to test both to choose which one to use. We saw immediately that we should use the multiplicative version since the seasonal level scales with the overall level rather than staying constant. There are 4 equations involved in this. The level, this adjusts the base level. Our low choice of alpha here gives less weight to recent observations. The trend, this captured the long-term upwards or downward slope of the data. Our choice of beta here also gives more weight to the historic trend rather than recent anomalies. The seasonal, this updates seasonal patterns based on the ratio of actual to predicted value. Our very low choice of gamma here assumes a stable pattern throughout. The forecast equation uses the other 3 components to project future values. On the left, you can see a decomposition of our data into the trend, seasonal, and residual components. The trend suggests an upwards pattern, and our model on the right predicted this. We expect Memphis's ongoing industrial expansion to intensify, assuming the lack of a major climate change prevention. The results also captured the relative insulation of the sector from population decline, unlike the residential. To analyze the sensitivity of our model, we applied plus or minus 1% Gaussian noise and forecast for 20 years. This yielded an R-squared value of 0.9975. The fact that this is so close to 1 indicates that the model is resilient and precise. We also analyzed the residuals in 2 ways. Over time, on the left, they appear randomly distributed around 0. The fact that there's no visible pattern here is a strong indicator of model accuracy and lack of bias. As a histogram on the right, with an overlaid kernel density estimation, the distribution is centered near 0 and closely follows a normal distribution. This really confirms the absence of systematic error. Overall, our predictions for question 2 are shown. Although the residential energy usage will decrease over time, the industrial is clearly a dominating increase. As a city, Memphis's popularity in manufacturing and transport industries is growing, with many leading tech companies recently choosing it as the location for constructing huge manufacturing facilities, including a major new data center opened recently. So, the graph follows our reasoning that industrial and commercial power will increase and dominate. A major strength of the model is that by splitting the data up, we were able to expose separate trends, both for residential and commercial, by using the 2 different models. If we just modeled total energy usage directly, the trends we noticed would have cancelled each other out. This also allowed us to make separate predictions for residential and commercial, which would potentially be more useful in a real-world application. Now I'll hand over for question 3.
Question 3 tasks us with coming up with a vulnerability metric for neighborhoods in Memphis, Tennessee. The metric that we decided to go with was expected economic damage. Simply put, the expected economic damage of a neighborhood is the expected damage that a neighborhood would incur given a heat wave. We consider both the probability of a power outage as well as if a power outage doesn't actually happen. We later determined this to be dependent on certain grid features that we find. If there is a power outage, we expect transport networks to fail and the failure of network services in the neighborhood, and therefore the loss of the wages for all individuals within the neighborhood. If there isn't a power outage, we expect people to work from home as per CIPD data, and the main cost to be the cost of cooling. So now onto the considerations for a vulnerability metric. We think that the two main considerations for a vulnerability metric is to be policy ready and actionable. We think that policy ready means that it is easily understandable for non-expert policymakers. We think if we use a simplistic method like normalizing between 0 to 1, what does 5 mean, 1 to 10, what does 5 mean relative to 1? Is it 5 times worse, 50 times worse, or 500 times worse? In the case of in terms of economic damage, it's firstly immediately intuitive and visceral, and also you can easily compare the economic damage between two neighborhoods. Secondly, on being actionable. Later, we use this data to place emergency centers within Memphis, Tennessee to protect the most people. We think that economic metric is intrinsically linked to opportunity costs. Let's say an emergency center costs $2,000, but it could potentially protect $5,000 worth of economic damage. This helps government policymakers actually consider the weight of their actions and also to consider the optimal allocation which we'll later present. So firstly, on determining the power outage probability. We focus on a small part of the grid of substations. Substations route electricity throughout areas, specifically neighborhoods in Memphis, Tennessee. And we think that the more substations there are, there's a lower probability of grid failure. From National Grid research data, we get the working radius for each substation to be 2,000 meters. And from the same research, we also find and estimate the probability of outage to be between 0 to 0.3 and also linear to the number of substations based on MLGW historical outage data. In practice, we make an API query to the OpenStreetMap service, and we process each of them and add them to the map using the Python Folium library. Here are the calculated power outage probabilities. In terms of weight, take a pretty simple approach, and we find the average income that would be lost per person during a 6-hour outage duration. This is also gained from MLGW historical averages. We multiply this by the employed population and get the following result by neighborhood. Clearly, there is a very large range in the lost wages between neighborhoods. East Memphis will lose 1.68 million if there isn't a power outage, and South Forum will lose 115,000. The large range of values strongly motivates an optimized approach, as simply placing an emergency center next to each neighborhood would not adequately protect people, especially when we consider the resource constraints that the government deals with. In terms of calculating cooling costs, why should we model cooling costs? We think it's very important as it accounts for 40 to 60% of summer electricity bills, and it also encapsulates economic vulnerability. To do this, we basically adapt the model that we gain in question 1 and also add an HVAC term. In practice, this looks like adding an if-else statement that if the temperature is greater than 27 degrees, which we found from previous research to be the temperature at which Memphis residents begin to switch on their air conditioning units, that air conditioning unit switches on, which decreases the temperature. In practice, this looks like the temperature spiking down at certain points. And based on the amount of time that the air conditioning unit is switched on, we can calculate the cooling cost based on the cost of energy as per what we calculated in question 2. So in terms of neighborhood vulnerability scores, we see quite a large variety. One would expect affluent neighborhoods to dominate the table, but we actually think that the most clear pattern is that the neighborhoods with the highest economic damage are those that are the most lived in. So we actually think our metric protects the most people.
So we didn't actually stop at giving vulnerability scores, because this does not tell the local government how to act. And we decided to develop an algorithm which will tell where to place emergency centers. So we're given the position of neighborhoods, E-value, which is an expected economic damage, and which is the number of emergency centers. We say that an emergency center is effective if it's placed within distance R from the city. We took R equal to 2 kilometers to be reasonable. Then we reduce the financial loss by 30% if the emergency center is within the radius. This is a US Army power restoration statistics. You can see an example below. So now we will consider the points where a hypothetical emergency center can be placed. Drawing a circle of radius R around each town, we put one town in each region of overlap between 2 or more circles. For each circle, we also randomly place a point within it without overlaps. We do this using Shapley geometry model in Python. Then we simulate placing one emergency center at each of the points and compute the total score after placing this imaginary point. Then we place one, which minimizes the sum at current iteration. Then we update the total economic damage and repeat this process n times. Why is this algorithm good? It gives us near optimal placement in many cases. We suspect that the problem is NP-hard, similar to K-median problem, which is known to be NP-hard. So we think that we found the best solution that can run in a reasonable amount of time. It is important to know that by framing everything relative to the economic cost, we're aware of the government's resources. We then use technical computing to determine the best allocation. Our solution is also versatile, which makes it a good solution in terms of technical computing. So here are the results of our algorithm. As you can see, we have some emergency centers, and they are not placed in the most rich neighborhood, as one might expect. So they are actually equally distributed around the city, which looks reasonable and justifies our algorithm. That is the end of our presentation. Thank you very much for your attention.
I can start with a question. So I love the mapping you did for Q3, and I think you used it in two ways. One was like placing these centers, and then also this power substation thing. You were mapping number of power substations to probability of a power failure. Can you walk me through the link there a little bit more clearly? Like, one thing you mentioned is some neighborhoods have more people than others. Actually, I think those were often your more vulnerable neighborhoods. Is the number of substations like just a function of the number of people there? Is it a meaningful metric for the chance of a power outage?
I think from a grid standpoint, like on a practical standpoint, the number of substations that are present definitely has a linear, like an effect on the power outage. And we did see in many cases that the number of substations that are present is also dependent on the number of people in the area. But we think that it's in residential neighborhoods that it's damaged. But substations may also be put to like protect businesses, and that actually results in damage to neighborhoods, especially because a lot of the areas, of course, like bid rent, are placed. Like commercial areas won't be the same as the residential areas.
Okay. So if it could be that a power substation was placed because there's a big industrial area
Yeah.
that helps the surrounding neighborhood.
Yeah.
Okay, that makes sense. Thank you.
Yeah, I've got a couple questions about the vulnerability score, in particular around the calculation for lost wages.
Yeah.
So I'm, in terms of power going out in a particular area, why does that necessarily mean that the people there are going to lose wages and not work?
Oh, we expect the transport links to fail within that area, and those people would not be able to go to work. Of course, the alternative to that is working from home, but we think that if there is a power outage, networks would fail, and it wouldn't be sustainable for businesses to ask people to work from home if there is a power outage.
Okay, and then one to follow up there. In terms of lost wages, a more affluent area, you'd expect people to be making more wages and have a bigger vulnerability score because of that.
Yeah, I think we do concede this. I think part of the economic metric, obviously a drawback of this is that certain more affluent areas will take like a higher score because of higher wages. But we think this is a trade-off because what we actually result is that we can protect the most people. And I also think there's some other separate economic factors, which means that if general economic like wellness is maintained, it can actually benefit the rest of the city. That's another factor which isn't easily modeled, but I think it's a consequence of using economic metrics.
Okay, in part one of the challenge, you did mention a very interesting limitation that other teams didn't. The temperature likely is not uniform across the dwelling. So how would your model be adjusted to account for this limitation? Do you need more data? Would you include more variables? How would your model change?
Sure, so I guess we'd use, we would need more data for the inside, and we would calculate the dimensions and also consider heat flow between different rooms. We could also have a gradient of temperature, especially for high buildings, this would be useful. So we could have the temperature changing as you go up the building. So that would definitely be the things we'd take into account.
Also, like, I think aspects such as wind speed is affected by several complex factors, like the houses in the vicinity and naturally the height. And this wouldn't really be possible given the data.
Okay, yeah, thank you.
Nice presentation. In part two, you use the two different models, right? did you actually implement a single model, or try to approach for a single model at all?
Yeah, we did. So we tried to use the Surima model like on the original time series, but we think that the lack of seasonality, because as shown, let me just give me a second. For the industrial section and the residential section, the seasonality is completely different. So when you add them together, it kind of cancels out in a sense. And so when we tried to do it, it didn't pass the test that we were given. And we thought intuitively they must follow different demands, so we tried to separate them. And once we did that, the trend was obvious.
I want to ask a follow-up question about that. Can you go to the plot that shows the trend for the industrial?
Or presentation.
Sorry, I know it's slow.
It means the slide with the left and
Or
right.
no, I meant the one you had. I just saw it, but maybe I can explain it. It was the one where you're showing like you show about 3 seasons of industrial data, and then you extrapolate out for the forward, and you have this strict increase, like a pretty steep increase in industrial usage. Keep
The
going.
whole winter's result.
No, keep going. Sorry,
Yeah.
it's the next one.
Sorry, that's quite a lot of lag.
Forward. Yeah, I know it's okay. This one. Okay, so to me, when I look at this data, if I just eyeball it, it looks like we're predicting a strong increase in usage off a relatively small amount of data. So I worry about the sensitivity of this model. Now, you did do a sensitivity analysis. You added some Gaussian noise, but you used a very small variance on that Gaussian noise. Like I think you said it was like a 1% of the magnitude or something. So I want to ask how you chose that variance. And say you were presenting this to like, I don't know, a decision maker who had to make decisions about this sort of stuff. How would you convince them this is a believable trend?
I think in terms of the Gaussian noise, I think it's relatively subjective to pick what the Gaussian noise value is. But I think potentially we could have like fell victim to some kind of like post hoc analysis because of things like data centers and like current affairs effects that would promote like higher industrial usage in the future. We might have been convinced that a high increase would be justified, but I do concede that the extent to which it will increase is kind of dependent on several other factors that we can't predict.
Okay, that's a good answer. Thanks, guys. So if you want to do a quick thank you, go for it.
Yeah, sure. I just wanted to say a quick thank you to everyone involved. So, I mean, firstly, team members, not only Victor and Andre, but also Henry and Yuya, who unfortunately weren't able to make it today. We're also extremely grateful to our school, Winchester College, and our coach for helping us and supporting us through every step of the journey. It's been great. And finally, to everyone involved in the organization of M3 Challenge, so Jane Street, the hosts, the judges, and everyone from SciAm for organizing this. It's been a great opportunity and a brilliant experience, so thank you for having us.